Welcome, ladies and gentlemen. So what I'd like to do is show you how to verify trigonometric identities when we have rational expressions either on both sides or just on one side. So remember, when verifying trigonometric identities, basically what we're trying to do is verify that the left side is equivalent to the right side. And you can look at all these examples I have up here, and it's not very obvious that one side is obviously equal to the other side. So we're going to have to do a little work. Now, in my previous videos, we kind of worked on a step-by-step, always choosing the most difficult side. And usually the most difficult side was one that contained fractions, or a rational expression, or that had operation like adding and subtracting inside of it. And basically what we did was we worked on that side by either eliminating the fraction or by applying the operation. Well, the difficult thing with this one is you can see that here both sides, more often than not, combine operations as well as fractions, or are both rational. So therefore, not always are we going to pick the best side that's maybe going to make it the easiest. So I'm going to work through these problems, and when I go ahead and explain everything that I'm doing, it's going to be basically through the perception of what I feel is going to be the best way to work through the problem. However, just because I'm choosing to work on one side or using certain identities doesn't mean you have to use that. What's nice about verifying identities, and also what's sometimes not nice about it, is there's multiple different ways to arrive at your answer to verify the identity. So just because I'm showing one way doesn't mean that's the only way to do it. All right, so let's go ahead and get started here. And in my first example, I have 1 over sine of x minus 1 over cosecant of x equals cosecant of x minus sine of x. Now, at first you might say, all right, well, I have fractions here. I want to get rid of the fractions, right? That's what you always said. You can see that both of them are subtractions, so I don't really want to combine them because I want them to remain as as fraction, or I want them to remain as a subtraction problem. But one thing I also notice is, by understanding your reciprocal identities, or reciprocal functions, you can see that 1 over sine of x is the reciprocal of cosecant of x. So basically what I could do here is rewrite 1 over sine of x as cosecant of x, and write 1 over cosecant of x as sine of x. And you can see that is verified. Now, in these examples, what I'm going to do is I'm going to often keep, I'm not going to write the right side here. Like I did in the other problems, I said, always keep the right, always write both sides. But here you can see these are pretty these are pretty extravagant expressions. So it's going to take a little time to always write both sides. So I'm just going to keep my equal sign, keep on going until I've arrived at a verified expression. Somebody new in school? OK. So let's go ahead and work on the next one. On the next one, I have cosine of theta times cotangent of theta divided by 1 minus sine of theta minus 1. Well, and that's supposed to equal cosecant of theta. So you can see here I have a fraction and an operation. Well, the first thing, we got to take this. This is obviously the more difficult side. We want to take this and make it look like that. So the first thing I see is, well, minus 1, that's not going to work, right? I got to combine those. So I got to make sure I have the common denominator. So the common denominator here is going to be 1 over sine of theta. So I'm going to multiply 1 as 1 over sine of theta. Actually, let's just write it. Let's just write it out. I'm going to rewrite 1 as 1 over sine of theta times divided by 1 over sine of theta. So it's going to look something like this. Cosine of theta times cotangent of theta all over 1 minus sine of theta minus 1 minus sine of theta over 1 minus sine of theta. Now, by doing this, what you can obviously see is now my denominators are exactly the same, so I can combine them. And then I'm just subtracting my numerators. So therefore, I'm going to come up with cosine of theta times cotangent of theta minus 1 plus sine of theta. I'm distributing this negative sign, right? Because basically you're subtracting the whole quantity. So it's going to be minus 1 and then plus sine of theta all over 1 minus sine of theta. Now again, oops, and I'm not even following my rule. You got to make sure you keep on improving those equal signs. Now, again, I'm looking at something it's still really not making anything more simplified. Ooh, cosine over sine. I could rewrite this. Let's rewrite this. Cosine theta times cotangent. Let's rewrite cotangent theta as cosine over sine. OK, so I'm going to rewrite that, and I'll explain why I'm going to do that in just a second. All right. So now in my next example here, again, what I need to do is I still need to get this down to cosecant of theta. So I can't have 1 minus sine of theta. Now, what I can do here is, one thing I look at that is I can look into multiplying by multiplying everything by sign. And as long as you multiply the numerator and the denominator by sign, then I can get sine off the denominator over here, and then we'll see what kind of happens. So what I'm going to do is I'm going to multiply by sine of theta in the numerator, and you have to multiply it in the denominator. So when I multiply it in the numerator, here I multiply this expression, the signs divide out, so I'm left with cosine squared of theta minus sine of theta plus sine squared of theta, right? Because you got to multiply by everything. And then in the denominator, I'm left with sine of theta minus sine. Oops. Let's rewrite. Let's keep that. You could multiply that out, but I am just going to leave that out there so I don't have to do extra work later. OK. So now what you see here is I have cosine squared of theta plus sine squared of theta. Well, remember, cosine squared plus sine squared equals 1. So these go to 1. Then I'm left with 1 minus sine of theta, which is the same as 1 minus sine of theta. So those divide out, and I'm just left with 1 over sine. Well, 1 over sine is the same thing as cosecant. So therefore, that is verified. All right. So I kind of ran out of room, so I had to kind of talk it as well instead of showing it. But just make sure you multiply by sine by every single term. When multiplying by sine here, those cosines go to cosine squared. The sines can't divide into 1 here. That goes to negative sine. That goes to sine. I didn't multiply that through because then I'd have to divide it back out. Cosine squared plus sine squared goes to 1. So therefore, I'm left with 1 minus sine squared, which is the same as this. So those divide out, and I'm still left with a 1 up top. So 1, because even when you divide everything out, there's still a 1. So 1 divided by sine is equal to cosecant. Good. For the next example, again, you have cosecant of t minus 1 divided by cotangent of t equals cotangent of t divided by cosecant of t plus 1. And this one can say, well, which one's more complicated? They're both like exactly the same almost, right? This one has a binomial denominator. This one just has the monomial. So the best thing that I can think of is, well, if I need, I'm going to need to, if I want these to get to be the same, I know that cosecant and cotangent are related in their Pythagorean identities. And it's probably going to be easier for me to rewrite cosecant of t plus 1 as cotangent, or at least this as a one single term, if I use the difference of two squares. So I multiply by cosecant of t minus 1 on the top and the bottom. OK, so what that produces here is cotangent of t times cosecant of t minus 1. I'm not going to distribute it yet. Well, this becomes cosecant t plus 1 times cosecant t minus 1 by using the difference two squares becomes cosecant of t, or cosecant squared of t minus 1. Well, cosecant squared of t minus 1 using your Pythagorean identities is the same thing as cotangent squared. So I have cotangent of t times cosecant of t minus 1 divided by that now becomes cotangent squared of t. Well, cotangent t divided by cotangent squared of t, that can divide out, leave me with just, not cotangent, leave me with cotangent squared of t. Those divide out, just leave me with the cotangent of t. So therefore, I'm left with cosecant of t minus 1 divided by cotangent of t, which you can see is exactly what I have on my left side. So you don't always have to work on the right side or always work on the left side. Just choose a side. And again, you could have worked, could have done some other work on the right hand on both sides and arrived at the same verification. Now on this side, again, what we're trying to do, we're trying to make either the left side or the right side, look like the other side. And this one, I automatically see this cosine squared theta plus 4 cosine theta plus 4. I'm like, that looks really confusing. But so I'm probably going to want to work on this side rather than trying to read 2 secant of theta plus 1, trying to make that look like that. That just seems even more complicated. So one thing that I look at this is I automatically see factoring. And if you don't see factoring, replace the cosines with an x. So if I looked at that as x squared plus 4x plus 4, I say, oh, that's factorable as x plus 2 times x plus 2. Or x plus 2 squared, right? So I can do the same thing with my cosines. I can factor this as cosine of theta plus 2 times cosine of theta plus 2. That's all over cosine of theta plus 2. Well, now you can see that the cosine of theta plus 2, those divide out. And now I'm just left with cosine of theta plus 2. Well, we have an issue, because that's still, now that's a single quantity, and we're supposed to get a fraction. So that doesn't even look anything like secants either. So again, kind of going back to what I did over here, sometimes to make them the same, you got to just multiply by a multiplier. And I didn't explain it over here, but as long as you multiply by the same term in the numerator and denominator, you're not changing the fraction. For instance, if I had 1/2 and I multiplied by 4 on the top and the bottom, I now obtain 4 over 8. Well, 4 over 8 and 1/2 are equivalent fractions, OK? So it works with numbers, and it works with trigonometric functions as well. I want to get a secant in the denominator, and I want secant to be in the numerator. Well, to get secant in the denominator, I can look at this as a fraction, as cosecant of theta plus 2. And I can multiply by secant of theta in the top and in the bottom. Just make sure when you're multiplying by secant, you got to multiply by both of them, kind of like how I had to do here. You got to make sure you apply distributive property to all your terms separated by subtraction and addition. Here, these two terms are subtracted by addition. Well, secant times cosine, those are reciprocal functions, so that goes to 1, or that multiplies to 1. So, and then secant times 2, I end up 2 secant of theta plus 1 divided by secant of theta. And you can see that's exactly what I have over there. So now that is verified. On this next example, I worked on this one a lot of different times. There's a lot of different things to go over. First thing I tried to do was do what I did over here, multiply by the conjugate to try to get a difference of 2 squares. But the problem with doing it that way was that gave me a single quantity. And I don't want a single quantity over here. I want 2 terms that are separated. Then I tried multiplying by the conjugate of cosecant of x plus secant of x, which would have been cosecant of x minus secant of x. But that just made everything so much more complicated. And it really didn't help me arrive at cotangent. So, and that's one of the main important things I want you to do is, keep on trying these problems. You might try one side and get nowhere. So then go to the other side. You might get nowhere. So then maybe think of like different identities, different operations, different things that you can do. I might make it simple because I've worked through these problems, so I kind of know where to look at. But I was just like you when I first started these problems. I didn't know where to start, where to begin, so I just started trying things. And that's basically one of the most important things. Just try, see how far you can get, and then try something else, try something different. So what I finally came across was, well, why don't I try to combine these, cosecant of x plus secant of x, and just see what happens. Even though I don't want them as a single quantity, let's just go ahead and combine them. Well, to combine them, it makes sense to rewrite them in terms of sines and cosines. So I basically have 1 over sine of x minus 1 over cosine of x divided by 1 over sine of x plus 1 over cosine of x. So if I was going to go ahead and combine these, basically I got to get common denominators, which common denominator is going to be sine of x cosine of x, or the common multiple. So I multiply these by cosine of x over cosine of x, sine of x over sine of x, cosine of x over cosine of x, and sine of x over sine of x. OK, so now by doing that, now what I obtained here is, let's write the problem over here. So now I obtain cosine of x minus sine of x divided by your common denominator of cosine of x sine of x divided by cosine of x plus sine of x divided by cosine of x times sine of x. And you might say, all right, well, you just made this look like it's so much more complicated. It's not even close to looking like that, right? Well, yeah, you're right. However, I have now at least I've written this down where I have a fraction divided by a fraction. And remember, when you have a fraction divided by a fraction, you can eliminate the fraction in the denominator by multiplying by the reciprocal. So then what I do is I multiply by the reciprocal of my denominator, which is cosine of x times sine of x divided by cosine of x plus sine of x. And I do that in the top, and I do that in the bottom. And by doing that, what I notice is that goes to 1. And then what I notice is now these also divide out. And then I'm left with a cosine of x minus sine of x divided by cosine of x plus sine of x. Man, I'm getting really bad at keeping my equation signs, equal signs there. OK, Well, again, this still isn't cotangent, right? Well, you're right. But again, it goes back into this. Is there maybe a function that I can multiply by to arrive at cotangent? And it ends up being cos, because remember, cotangent is cotangent over sine. So if I multiply by 1 over sine, then that will take this 1 over sine times sine will take me to 1. And 1 over sine times cosine will take me to cotangent. Well, the same thing as 1 over sine, the same thing as multiplying by 1 over sine would be multiplying by cosecant of x. So I multiply by cosecant of x on the top and on the bottom. And remember, you have to apply distributive property. And by doing that, what I finally get is cosecant of x times cosine is cotangent of x minus 1 over cotangent of x plus 1. And you can see that it is verified. Hopefully that shows on my video. I'll have to go back to my camera. OK, so in the last one here, obviously we can determine what's the most common, what's the more difficult side. It's the left side. And obviously we need to combine these down to one single quantity as 1. So unlike here, where we didn't really have to combine them, see, the reason why we didn't want to combine them is because we want it to look like the right side, which wasn't combined. Here, obviously they're combined to 1, so we got to combine them together. So to do that, we got to get common denominators. Well, common denominators in this case is going to be sine of x plus 1 times cosecant of x plus 1. So I multiply that on the numerator and the denominator of both sides. What am I doing? That's multiplying by the same. So I multiply by cosecant of x plus 1 times cosecant of x plus 1. And then I multiply over here by sine of x plus 1 over sine of x plus 1. So therefore, I now arrive at cosecant of x plus 1 plus sine of x plus 1 all over cosecant of x plus 1 times sine of x plus 1. All right, and we haven't really got too far, right? Crap. But one thing, we still can do an operation. Now, I don't really want to add these two, because by adding, I got to get common denominators again, and it can bring up a whole different issue. However, what I can do is apply FOIL, or distributive property here. And by doing FOIL, or distributive property, I can multiply those out. So when I do that, I end up with cosecant of x plus 1 times, cosecant of x plus 1 plus sine of x plus 1. The numerator and denominator are the same here. And then when I multiply these out, cosecant of x times sine of x, cosecant of x times sine of x is equal to 1. Cosecant of x times 1 is equal to cosecant of x. Sine of x times 1 is equal to sine of x. And 1 times 1 is equal to 1. Now, before even combining, I don't really need these parentheses anymore. And what you can obviously see is it's the exact same expression. They're kind of switched around. Everything's moved around. However, it's the exact same expression in the numerator and in the denominator. So therefore, those all divide to 1, which then makes our identity verified. So there you go, ladies and gentlemen. That is how you verify identities when dealing with rational expressions on one or both sides. Thanks.